Thanks again for the invitation. And I would like to say that my work is a lot less mature and not as detailed as the previous talk, but I hope that it will give you some insights, as an example how end users, model developers are starting to use EarthCARE data. So I'm not part of the EarthCARE community in a more narrow sense. I'm really just downloading data and using it. Here the motivation. So the broader goals are to make use of EarthCARE for the model development of the ICON model at DWD. And of course, for this, we have to know more about the data and the products. So today, I'll give you some insights in what I started doing. First, I started to compare the EarthCARE radiative fluxes with the series products, which is what I've used before for radiation validation. And then we dive deeper into clouds by using the ACM CUP products to look at clouds in ICON. And this we do already with an example really from model development side by comparing a 1-moment and 2-moment representation of the cloud ice in ICON and how we can use EarthCARE to learn about these different model parameterizations and how they represent clouds. So let's start with the radiative flux data. So for this, I used the BBR level 2B data from July 2025. This BA baseline, as you call this, and a full month of EarthCARE frames. And we are specifically looking at these combined top of atmosphere fluxes for solar and thermal. This is then mapped onto the ICON grid just by a nearest neighbor mapping or looking for the ICON grid cell that contains the EarthCARE data on a model time step of 120 seconds. And here I present only data with quality status 0. And as a reference, we use the series level 2 data, so the SSF data. This is currently, or for this month, available from 3 satellites. And here we use a 20-minute ICON output, so not for the full resolution, but for the radiation data, which is radiation is only called every 20 minutes in ICON anyway, so the 20 minutes are really sufficient. And in addition, we also use a level 3 data from series, that's the SUN1 DEC, which includes data from geostationary satellites, but has the advantage that we get full global coverage and at the same time hourly data with the full diurnal cycle. On the other hand, it's only 1 degree, but it's very useful data set as well. So the ICON configuration is close to our operational global model. It's a so-called R3B7 icosahedral grid with 120 levels. So this is roughly 12-kilometer grid spacing. And for this, I kind of reforecasted July 2025. And we look at 6 to 30-hour lead times for each day, which then gives us the full month. We use the ECRAT radiation scheme as in the ECM model, but with a older Tegen aerosol climatology. The convection scheme is also very similar to ECMWF's IFS model. Then I will show you results from the 2-moment cloud ice scheme, which also predicts the number of cloud ice particles, not only the mass, but I will also show one moment for reference. For the 2 moment, we couple the clouds consistently with the radiation through effective radius. And for cloud droplet number, we use the MODIS CDNC climatology, which at least gives us some estimate of a TUMI effect, but it's also coupled to the precipitation formation. So let's look first at a coverage from EarthCARE versus CIRRUS. And as most of you probably know, CIRRUS is also scanning to the side. And by this, a monthly data set gives us full global coverage, except for, in this case, Antarctica, whereas EarthCARE, looking only nadir, basically gives us a much thinner coverage, and that's of course a challenge when we want to compare these two data sets, or when we do statistics. We cannot simply ignore these different sampling properties of the data sets. This is to show you EarthCARE frame and how it compares with ICON, just randomly selected. Here we see radar reflectivity to give you an impression how the clouds look like from EarthCARE and from ICON with a PALMTRA forward simulation. And in the top figure, you see the corresponding radiative fluxes with a long wave in blue, axis to the right, short wave in red, axis to the left, and the solid lines are EarthCARE, dashed lines are ICON. This only to give you a bit of a visual impression how good the model is, that it captures the general cloud structures and their impact on the radiative fluxes. I'm sure you have seen similar plots from the IFS or other models, and ICON is not very different. But this allows us to do some interesting statistics, as I think. Here you see the zonally average top of atmosphere radiative fluxes, only shortwave. So basically the reflected shortwave at top of atmosphere. And the plot is a bit crowded, but I will walk you through it. Different colors correspond to the different observational data sets. So blue is EarthCARE, red is CIRRUS SSF level 2 data only from NOAA 20, and the magenta line is the level 3 data from CIRRUS that combines all the different data sources. And the solid lines are always the observations, and the dashed lines are the two ICON configurations with 1 and 2 moment microphysics. So the important thing here is that you see how the different, the color, the lines of the same color basically line up quite nicely. So the ICON and the corresponding observations match quite well, as it should be. And where the red lines deviate from the blue lines, and all the red lines deviate from all the blue lines, then this is clearly a difference in sampling, because ICON also shows this, and ICON is sampled consistently with each observing system. So when we have this configuration that all blue and all red is together, this indicates that the difference is due to sampling. But we have other regions, for example, here in the between 50 and 60 north, there's clearly the dashed ICON line. So the, or actually both ICON lines here deviate from the solid line. So here we have a clear bias in reflected shortwave in ICON. Interestingly, the blue lines are still closer together. So this is kind of interesting, and it could be interpreted as an EarthCARE bias, which is kind of at first difficult to understand, because you would argue, oh, the solid blue line and the red blue line are close together, so EarthCARE and Sirius measure basically the same thing. But when we look at ICON, where the different lines in the blue and the red lines differ, we can see that there are potentially sampling effects, and those we don't see in the observation lines. So because the difference between the red line is bigger than the difference between the blue lines, that actually points to a potential EarthCARE bias compared to Sirius. Or you could turn it the other way around. Maybe Sirius has a bias and EarthCARE and ICON, which agree fairly well, are fine here, but I would still tend to say that Sirius is our gold standard, and we should think more deeply what ICON and EarthCARE are doing in this region. In the Sun1 DEC, so in the level 3 product, we have a fairly good agreement, but also this bias in 50 to 60 north also is reflected in the full diurnal cycle and the full data set. So this is important to look at. It's not just at local noon where we have the polar orbiters, but it's also visible in the full data set. So this is an important issue. And of course, the full mean of the full diurnal cycle is lower than just what we get from the polar orbiter. That's also easy to understand, but an important message. Having this data, we can now do interesting exercises, as I think. For example, we can now look at land-only pixels, and there we find now a significantly better agreement between model and observations, but also between the observations themselves. So over land, the situation is better. Over sea, we see the similar behavior as in the total data set, which points to the fact that most of the difference we see come from maritime clouds, which we know is difficult. So just to give you an idea about this 50 to 60 north reflected shortwave bias, that's not coming from some boundary layer clouds or something, but it comes really from a bigger frontal system. So this is comparing actual Sirius spatial data overpasses with ICON. Here you see different Sirius instruments. So all the various satellites are plotted on the same plot. And you can see that in this frontal cloud bands, ICON simply reflects more than what we see in the corresponding Sirius data. And this is exactly the signature that we saw in the zonal averages. That would be a corresponding cross-section or frame from EarthCARE through one of these frontal maritime clouds. And the cloud in ICON actually doesn't look particularly strong or overemphasized, but nevertheless, we have this positive bias in reflected shortwave. So it seems to have something to do with the optical properties of these clouds. In the long wave, the agreement is at first better, but that's of course also because there's less variation in the long wave. But you can see that dashed lines are grouped at the top. So ICON has a positive bias compared to the observations, and you can see that the blue solid lines is lower than the red lines. So EarthCARE seems to be low biased compared to Sirius. And we look at this a bit more detail later. Exactly, we can now just do the statistics or the plotting a bit different and change from these zonal average to these error statistics at individual footprints, basically. So here we have bias RMSE for the full data set and then decomposed in clear sky ocean, all sky ocean, clear sky land, and all sky land. And this is again reflected shortwave. And you see basically the same thing, but now we can look at all the three different Sirius instruments and compare them with EarthCARE and with ICON. And you can see that first of all, ICON has this positive bias in reflected shortwave. That's also in clear sky and especially over the ocean, but not less so over land. But you can also see that EarthCARE groups very well with the various Sirius instruments. So it's not a clear outlier. So there's some variability also between the Sirius instruments. And so here I would say EarthCARE is consistent with the Sirius data. That's now the picture for mid-latitudes where we had this 50 to 60 north biases. And here you have this interesting effect that ICON has a positive bias compared to Sirius, but less so compared to EarthCARE. And as I said, I think we should see that more as a EarthCARE and ICON may have both biases, probably for different reasons, and Sirius might be probably correct, but we don't know. And here the same for long wave mid-latitude, where you see this positive bias from of ICON compared to EarthCARE. So EarthCARE has a negative bias compared to Sirius. And it's fairly consistent everywhere. So it's not a specific region or And this is a long wave in the tropics where we also see this positive bias of ICON compared to Sirius, which is even stronger for EarthCARE, again showing a negative bias of EarthCARE compared to Sirius. And again, fairly consistent, mostly in cloudy conditions, less so in clear sky. Okay, some intermediate conclusions for the fluxes. So in general, I would say we have a good agreement between ICON, EarthCARE, and Sirius, especially for shortwave top of atmosphere over land. But we have this interesting problem over the ocean, which is most pronounced in the Northern Pacific. And there, ICON is brighter than EarthCARE and Sirius, but also EarthCARE is a bit brighter than Sirius. So that would deserve some more attention. I can't give you a definite answer now why this is. In general, the EarthCARE thermal fluxes seems to be low biased compared to Sirius. Now let's look a bit more into the clouds. And as I already said, for that I will use the ACM CUP products, which combine the LiDAR, the radar, and the imager to retrieve some very interesting products like ice water content, liquid water content, and corresponding effective radii. The BBR is interestingly not an input to ACM CUP, but this should give us this possibility for radiative closure, but it's important to know that the radiative fluxes are not used in the retrieval. And here you have such a curtain plot for one frame, again showing you that ICON produces fairly realistic cloud structures. You can already see maybe a little bit to less blue, a little bit to less liquid water in the mixed phase region. But other than that, at first glance, it looks okay. So the reddish colors here now are the ice water content, and the blue is the liquid water content, but I unfortunately cut off the label bar for the blue stuff. So then let's move to the statistics, and here I do a similar thing as for the radiation. Zonal mean cloud statistics, but as we are used to from CloudNet, for example, I decompose this in a frequency of occurrence and an amount when present. So what you see are basically latitude versus height, cross section, and here a frequency of occurrence of ice cloud quantified by an ice water content threshold of 1 milligram per cubic meter. You see the typical picture with tropics, lower frequency in the subtropics, and then we see the mid-latitudes. And we have two corresponding icon plots from the 1 moment and from the 2 moment microphysics, which look very similar, but have a positive frequency bias compared to the observations. So we have too often cloudiness, too often ice in the tropics, little less so in the mid-latitudes. But in contrast, we underestimate the ice water content in the amount when present quite significantly. But I would say that's the behavior that we usually see in large-scale models. The cloud fraction or cloud cover is too high, but the clouds tend to be too thin, and EarthCARE confirms that quite nicely. For the effective radius, we can see that the observations show a fairly simple vertical structure with an increase in vertical or in effective radius going down. And here we have quite a difference between the two different microphysics schemes, with the 1 moment basically underestimating effective radius and very mixed behavior in the 2 moment, which even overestimates when the effect of the snow or aggregates starts to kick in. But at least it's interesting. From this, we can also estimate an extinction coefficient or some measure of optical thickness, which also then tells us that the clouds in ICON are basically too thin. So we have not a sufficient compensation between effective radius and ice water content. There might be a bit compensation, but it's not enough compared to EarthCARE. And now we can, instead of having this frequency of occurrence and amount and present, I show now also the actual zonal mean, which would be what's then relevant for radiation. And also in the zonal mean extinction, we underestimate compared to EarthCARE. So this is now really a bit worrying. So our ice clouds are not radiatively active enough. But I've shown you before that our fluxes are actually pretty good. So what's going on here? So what's going on is actually, you can see that when I do the same statistics for the liquid water content. For the liquid water content, we have a much too high frequency of occurrence in both ICON versions compared to EarthCARE, and the liquid water content or amount, now that's also the zonal mean already, not the amount when present, is fairly good in the right order of magnitude at least. So, so what we see is probably that we are compensating a lack of cirrus clouds or lack of ice water contents by having more liquid water. And that's really interesting to see from EarthCARE in these, with the vertical profiles and this ACM cup retrievals. So we had this suspicion before. So this is a forward calculation for MSG severi in the visible range. So the left plot is from the observations. So simply the severi disk. And next to it, you have the corresponding icon forward simulations. And you see that this is much too cloudy, especially over the oceans. It has this kind of milky touch, a little less with the new cloud physics based on the two-moment microphysics. But this already also points in this direction that over the oceans, we have too much liquid clouds, and this compensates our lack of ice water content. So to summarize, so we have a good agreement for the radial fluxes, especially over land. The two-moment scheme shows only very incremental improvements, but is basically very similar to the one moment. ICON has not enough ice water content, but compensates this by having more liquid. And actually, the story is a bit more complicated because when I developed the two-moment scheme, it immediately produced more ice water content than what we are used to have in ICON. And this gave me a lot of biases. And then I had to basically tune it down. So the model, microphysics model, would want to make more ice water content. But when I do that in ICON, then I get a temperature bias in the upper troposphere, especially in the tropics. And now having this information that the higher ice water content would actually be the correct solution, that points towards the kind of a new or extended hypothesis, which is also not very new, but that our deep convective heating profile from the convection scheme might be overly top heavy, giving us too much heating in the upper troposphere. And that forces us to have fewer cirrus clouds or lower ice water content. And then to have the correct radiative fluxes, we start compensating this with liquid water clouds. So that would be the more convoluted story. But it gives us a clear avenue for future development. So that's why I would conclude that EarthCARE provides really great data in high resolution and vertical structure for model developments, and such observations are, in my opinion, really crucial for making progress in especially aerosol cloud radiation interaction, but also in modeling in general. ICON demonstrates that it can do pretty well in a lot of variables, but of course we have biases. And these biases that can be clearly identified helps us to plan our development and focus our development. We come back to the old problem probably of the deep convection scheme, which also makes the evaluation difficult because you have always these contributions from the convection scheme, which are a bit harder to estimate. So my next steps in this, as I said, this is work in progress, will be to go more deeply into the cloud radiative effects and also include aerosol data from EarthCARE. So thanks for your attention, and I'm happy to take any questions.